Assalamualaikum warahmatullahi wabarakatuh.
We are from 10 group and we want to discuss about antenna and propagation.
My name is Ahmad Yahya Hasanuddin. You can call me Yahya. I come from Banyumas.
And my name is Desi Syafuddin Zuri. You can call me Rizky and I'm from Malang.
Before we start, I'd like to say thank you to Mr. Rudi, and because of your assignment, we know about this material about antenna and propagation. And I'd like to say thank you to my friend Zuhri. Without him, maybe this video, all of this material and this PowerPoint maybe cannot be done.
Okay, let's start discuss the material. Antenna is a device that serves of to transmit or receive electromagnetic wave or EM from the media cable to the air or device air to the cable medium. An antenna is an electrical conductor or system of conductor. In an antenna there is transmission radiates electromagnetic energy into space, and reception collect electromagnetic energy from this space. In two-way communication, the same antenna can be used for transmission and reception.
Next, good antenna. A good antenna has a good emission efficiency above 50%. A good antenna has an appropriate input impedance corresponding to characteristic impedance of the recording cable, or as the value are below than 2. A good antenna can radiate and receive radio wave energy with the direction and polarization depend on that application needed.
That is a picture from the antenna. Important parameter of antenna is there is a radiation pattern, polarization, efficiency, gain, input impedance, and also bandwidth.
So, radiation pattern. Radiation pattern, graphical representation of radiation properties of an antenna. Duplicate as two-dimensional cross-section. Beam width or half power beam width, measure of directivity of an antenna. Angle within which power radiated is at least half of that in most preferred direction. Reception pattern, receiving antenna equivalent to radiation pattern.
In the right side, there is a omnidirectional and directional antenna. There is a different from omnidirectional versus directional antenna.
Type of antenna. Type of antenna radiates power equally in all directions. Dipole antennas, half-wave dipole antenna or Hertz antenna. Quarter-wave vertical antenna or Marconi antenna. Parabolic reflective antenna used for terrestrial, microwave, and satellite application. Larger the diameter, the more tightly directional is the beam.
Antenna gain. Antenna gain is a power output in a particular direction compared to that produced in any directional by a perfect omnidirectional antenna, or that's called isotropic antenna. And antenna gain expressed in terms of effective area and relate to physical size and shape of antenna. Notes in here, an antenna with a gain 3 dB improve over the isotropic antenna in that direction by 3 decibel or a factor of.
Next, relationship between antenna gain and effective area. Here, the gain is belongs to 4P and E here belongs to effective area. So 4P times effective area divided by carrier wavelength to 2. For the example here, the effective aperture of 1.22 millimeter diameter parabolic reflector antenna is 55% of the physical aperture area. Compute the gain in decibel at 2 GHz and 4 GHz and the last 8 GHz. So the solution here, the effective area 0.55 or here is 0.55 here times by 1.22 divided by 2. So the result here is 0.643. So how to find the solution here? We will show you in the slide.
Propagation mode. In propagation mode there is a ground wave propagation, sky wave propagation, line of sight propagation. In ground wave propagation, follow contour of the earth can propagate considerable distance, frequencies up to 2 MHz. For example, this is AM radio. And on right bottom side, there is peak from ground wave propagation. And number 2 is sky wave propagation. In sky wave propagation, signal reflected from ionized layer of atmosphere back down to Earth. Signal can travel a number of hops back and forth between ionosphere and Earth's surface. Reflection effect caused by a refraction. For example, there is a amateur radio and CB radio. Like before, picture in right bottom side.
So the mechanism of this wave propagation we will show you in the slide.
Line of sight propagation is above 30 MHz. Neither ground nor sky wave propagation operate. Transmitting and receiving antenna must be within line of sight. This satellite communication signal above 30 MHz not reflected by ionosphere. Ground communication antenna within effective line of sight due to refraction, bending of microwave by the atmosphere, the velocity of electromagnetic wave is a function of the density of the medium. When wave change, medium speed change. Wave band at the boundary between medium.
So here the medium also change the speed of the wave. So like Zuhri said before, if there is the wave change medium, the speeds also change, and the wave band at the boundary between mediums, just like that.
Next, there is picture of line of sight propagation.
So in the picture here, there is transmit antenna and receive antenna, and the signal here is like the signal propagation and the mechanism.
Signal in here like a line, cross like a line.
Straight line.
In the line of sight propagation, there is a equation. And the first there is optical line of sight. It D equal to 3.57. Line of sight equation. First optical line of sight is D equal 3.57 power of root of H, and effective or radial line of sight D equal 3.57 root power of K times by H.
So here the D is belongs to distance between antenna and horizon. Usually is in kilometers like this. So then the H here is belongs to antenna height, usually in meters. So if there is not in meters, you should transform it to meter. So this is the optical line of sight, and this one is effective the line of sight. The difference here, there is K. K is belongs to adjustment factor to account for reflection. Rule of thumb K is 4 divided by 3.
Maximum distance between two antennas for loss propagation is 3.57 times by root power of kh1 plus root power of kh2. In here, h1 is h of antenna 1 and h2 is h of antenna 2.
So here there is like before, there is two antenna, transmit and receive. So here we assume that this one is transmit. So this one is belong to H1 and this one is belong to the receiver. So it's belong to H2 like this.
LUS various transmission impairment. First, attenuation, free space loss, distortion, dispersion, noise, and other effects like atmospheric absorption, multipath diffraction.
So attenuation, strength of signal falls off with distance over transmission medium. Attenuation factors for unguided media. Received signal must have sufficient strength so that circuitry in the receiver can interpret the signal. Signal must maintain a level sufficiently higher than noise to be received without error. Attenuation is greater at higher frequencies, causing distortion.
Free space loss. In free space loss, ideal isotropic antenna is like that. The formula is like that. In the formula, PT is equal to signal power at transmitting antenna, and PR signal equal to signal power at receiving antenna, and lambda in here is equal carrier wavelength, and d in here is equal to propagation distance between antenna, and c in here equal to speed of light. There is near close with 3 times by 10 power of 8 meter per second, where d and lambda are in the same unit. For example, meter.
So here, when we use C, if there is no lambda for carrier wavelength. So if there is no wavelength, we should use the speed of light. The speed of light is 3 times 108 meter per second.
Because why we should use speed of light, lambda in here is equal to the speed of light divided by frequency and power of square. In a satellite communication system applies the state of free space. The satellite is located at there is a simple exercise from free space loss. I want to read the question first. In a satellite communication system applies the state of free space. Satellite is located at an altitude of 36,000 km above the Earth, using a frequency of 4,000 MHz with a 15 decibel powered antenna, reinforcement of 45 decibel receivers antenna. At this question, we must calculate A, free space transmission loss or space loss transmission. B, power received when the emitting power is 200 watts.
So here is how to calculate. So like Rizky said before, PR divided by PT. So here we should calculate the decibel, the amount of L. So L here is 3.32.5 plus 20 log 36,000 plus 20 log 4,000. So the result here, the decibel is 196. After that, we should calculate the PR and PT. So in here, 15 plus 45 and minus by 196, and the result here is negative 136 decibel.
I think you will confused about this solution, but there is the formula from L reduce like that, and you can join this formula and this question. Free space loss accounting for gain of antenna. Free space loss accounting for gain of antenna is like that. The formula is like that. PT per PR is equal to 4P square times by P square divided by gain R and time by gain T time lambda square. This equation equal to write equation 2. QT in here is belongs to gain of transmitting antenna, and GR in here belongs to gain of receiving antenna. AT in here is effective area of transmitting antenna, and AR in here is effective area of receiving antenna. In the above formula, the power corresponds to that of the input signal at the transmitter and output at the receiver respectively.
So here I will give you some tips to answer the question or in our real life about free space loss counting for gain or about gain before. So here, if there is difficult to understand the question, it's better to you to draw it. So in here, always there is two tower, like two antenna. The first is the transmitter antenna, and the second is always belongs to receiver antenna. So if you don't understand the question, you should draw like small area for the first tower and the second tower. So it's called the effective area of transmitting antenna and effective area for receiving antenna. Yeah. So
Maybe like that.
after that, you should draw the line from the transmitter to the receiver. So because we draw, maybe you can understand the question or the problems in the real life.
Okay. Next is reduce formula from space loss accounting for gain of antenna. In here is L decibel is equal to 20 log lambda plus 20 log D minus 10 log AT times AR, and there is equal to minus 20 log frequency plus 20 log D minus 10 log AT times AR plus 169.54 decibel.
So here, if there is no lambda, you should use the second formula. So you should use frequency. If it's different between when you use the lambda and when you use the frequency, because here when we use frequency, the formula is minus 20 log frequency, but if you use lambda, it's 20 log lambda, like that.
Okay, next, path loss exponent. The free space path loss model is idealized by PT per PR equal A times the power of alpha. Here, the exponent depends on the transmission environment, like urban vs suburban, medium city versus large city, obstructed versus unobstructed, and indoor versus outdoors. Generally between 2 and 4, and obtained empirically. 2-ray, 10-ray, and general statistical model.
So here, when we use antenna or we use like propagation wave like that, we use it in our real life, and we make the tower in the real condition. So here we cannot hide from the environment in there. Like Zuri said before, the medium city and the larger city is very different, and it makes the it makes like the free space is different, and it will make the result different, just like in urban or in suburban, like that.
Distortion. Distortion in here is signal at the higher frequencies attenuate more than that at lower frequencies. Distortion is also set of a signal comparison of component in a frequency when it's distorted. And third form distortion is to recover the original signal set at the attenuation is equalized by amplifying higher frequency more than lower ones.
Dispersion. Electromagnetic energy spreads in space as it propagates. Consequently, bursts sent in rapid succession tend to match as they propagate. For guided media such as optical fiber, fundamentally limits the product XL, where R is the rate and L is the usable length of the fiber. Term generally refers to how a signal spreads over space and time. In here, the length of the fiber is effect to the dispersion, and it will make the difference in electromagnetic energy if the length of the fiber is different, like that.
Category of noise. The category of noise there is first thermal noise, second intermodulation noise, third crosstalk, and fourth is input. Thermal noise. Thermal noise due to agitation of electrons present in all electronic device and transmission media cannot be eliminated and function of temperature and particularly significant for the satellite communication. This amount of thermal noise to be found in a bandwidth of 1 Hz in any device or conductor. Its formula is N0 equal to K times by T. T in here is temperature, and there is temperature variable in Kelvin. And N0, the constant of N0 is watt per Hz.
In here, the K is belongs to Boltzmann constant, and the Boltzmann constant is 1.3803 times 10 to 10 power of 23 minus 23. And here, even though the T is big T, it is not time, but it is temperature. And if the temperature is Celsius or Fahrenheit, you should transform it to Kelvin. So, and in here, noise power density in watts per 1 Hz of bandwidth, and 0 belongs to density in watts per 1 Hz of bandwidth.
Nice.
Noise is assumed to be independent of frequency. Thermal noise present in a bandwidth of B Hz in watts and equal to K times T times B, or in decibel watts and equal to 10 log K plus 10 log T plus 10 log B, or here 10 log K is belong to 10 log Boltzmann constant. And there is other formula, just I said before, the Boltzmann constant is 1.3, and here the result is if you don't use the K, you should use minus 228.6 decibel watts. So the formula belongs to minus 228.6 decibel watts plus 10 log T plus 10 log P, like that.
Or we can go in this situation, take 10 log K or 10 log constant Boltzmann is equal to minus 2028.6 decibel volt. Okay, next. Noise terminology. Noise terminology is there is two part of noise terminology. The first is intermodulation noise. Intermodulation noise is occur if signal with different frequency share the same medium. And second is crosstalk. Crosstalk is unwanted coupling between signal path.
So this is the picture of the mechanism of noise terminology.
Impulse noise. Impulse noise is irregular pulse or noise speed and short duration and of relatively high amplitude.
Caused by external electromagnetic disturbance or fault and flaws in the communication system.
Other environment is atmospheric absorption and water vapor and oxygen contribute to attenuation. Multipath of the skull reflect signal to that multiple copy with varying delays are received. Diffraction, bending of radio wave as they propagate through the atmosphere.
So floating mobile environment. Fading here means time variation of received signal power caused by change in transmission medium or paths. So here is the mechanism of fading in mobile environment. So because in the picture here the receiver is mobile and move.
Multipath propagation or MP. Multipath propagation or MP in here is divided by three parts. First is refraction. Because the signal encounter a surface that is large relatively to the wavelength of the signal. Diffraction. Second is diffraction. Diffraction occurs at the edge of an interpretable body that is large compared to wavelength of radio wave. And third is scattering. Scattering is occur when incoming signal hits an object whose size is in the order of the wavelength of the signal or less. The effect of MP propagation. The effect of MP propagation is multiple copy of a signal may arrive at different pace. If pace add destructively, the signal level relative to noise declines, making detection more difficult, known as intersymbol interference or IC.
So here is the picture and the mechanism of the effect of MP propagation.
Types of fading. There is many types of fading. The fading is divided by seven part of fading. First is fast fading. Second is slow fading. Third is flat fading. Fourth is selective fading. Fifth is relay fading, and the last is Gaussian fading.
Okay, before we close our presentation and our discussion here. Again, I would like to say thank you. Thank you for watching this video. Thank you for your attention, and
and we so sorry if we have any speech false or other.
okay, I think that's all, and see you in the next discussion.
Okay.
Wassalamualaikum warahmatullahi wabarakatuh.